Hello, today we are going to talk about constraint minimization. In the last lecture, that is lectures 4a and 4b, we had looked at unconstrained minimization in finite number of variables. We had said that was a small detour from calculus of variations. This will also be a small detour, extension of that detour, where we are going to talk about constraint minimization in finite number of variables. This is the outline of the lecture. First we will discuss how constraints influence our objective function in terms of minimizing it, and then the concept of Lagrange multipliers, which is very important aspect of constraint minimization. Then we will learn what is feasible space when there are constraints, and constraints can be equalities or inequalities. Then this question of whether an inequality is active or inactive also needs to be dealt with. Finally, we will establish the necessary conditions for a constraint minimization problem. So, as part of this lecture, we are going to talk about constraint optimum when it lies on the boundary. Sometimes it is called a boundary optimum, because now the optimum, where it is a minimum or a maximum, lies on the boundary of the feasible space. We will derive the conditions for that and then talk about this local minimum and another concept called constraint qualification. And we will also see the sensitivity of the optimum point with respect to small changes in the constraints, and then finally the physical meaning of the so called Lagrange multipliers. So, let us look at a two variable problem, that is minimize f of x. As we see here, we are minimizing a function f of x with respect to x subject to an equality constraint. Is this a properly posed problem? That is a question we ask. Does it make sense? Okay. Let us look at that. Let us say we plot our equality constraint. Let us say I plot here h of x and this is x. Okay. It is an equality, right. So, that means that if I have h of x something like this, let us say, at how many points is it going to satisfy this equation? H of x is 0 here, 0 here, 0 here, 0 here, 4 points, that is all. So, our feasible space here is 4 discrete points. So, we cannot talk about minimizing f of x now, because if I look in the vicinity of this point, okay, let us say I am looking at the vicinity of my first point, which is feasible, meaning it has satisfy h of x equal to 0, there is nothing in the vicinity. When there is nothing in the vicinity, there is no way we can say it is a minimum or a maximum. That is, if you are running a race and only you are doing it, you cannot claim to be the first to come in the race, right. So, we can only compare with what is surrounding that point and then talk about whether it is a minimum or a maximum. So, here such a thing cannot be said when you have inequality constraint in one variable, because the space is not continuous. In order to talk about a minimum, we need to talk about continuous space, that does not exist here. So, this problem is not properly posed. So, what do we need? We need two variables, more than one variable, if we have one equality constraint. Okay. Now, h x1 x2 will be a surface, right. So, this will be a surface which is set at 0 value. Let us say imagine in we have two axes, let us say we have here x1 and x2. Okay. Now, h x1 x2 will be some kind of a surface, okay, some kind of a surface will be there, right. This surface has to be equal to 0. So, this surface is going to intersect this plane where x1 x2 will be some values. When it is at 0 value, there will be a closed curve, open curve, something will be there. So, on that point, then you have continuous set, right. Imagine a surface like we had talked about this bowl for a minimum, right. Let us say I cut it here, which corresponds to that h value being equal to 0. Everywhere else there are different values. Over here we will get a closed curve. On that closed curve we have 1 degree of freedom left, that is we had 2 variables x1 x2. Now this equality constraint makes that 2 variable space to a 1 variable space like that, or in general there will be curve like this. It can be closed or open, but there is going to be something. On that we will talk about minimizing this function f. Okay. This makes sense. When you have an equality constraint, then you need to have more than one variable. So, more variables are needed when there is an equality constraint. So, the simplest problem that we can think of in constraint minimization is one that has 2 variables. Here we are taking an example that I want to minimize with respect to 2 variables x1 and x2, a function which is defined as shown here, minus x1 times x2 subject to an equality constraint which is x1 plus x2 equal to 1. Okay. This is a simple problem. So, we are saying that find 2 numbers x1 and x2 such that their sum is equal to 1 and the product is actually maximized. So, if you notice we are minimizing minus x1 x2. So, that minus sign basically says that we are trying to maximize the product x1 x2, that we pose as minimizing negative of that product of x1 x2. Okay. Essentially this is maximize x1 x2 subject to, some people say such that both will be st x1 plus x2 equal to 1. If you pause and think about what solution it would have, you can try it out. You can say x1 is 0, x2 is 1, because you satisfy this constraint, then the product will be 0 because x1 is 0. You make it 0.1, 0.9, then it will be 0.81, and then so far, sorry, not 0.81, it is 0.1 times 0.9 will be 0.09, right, and then you can do 0.2 times 0.8, because you have to always make sure that this is satisfied, that will be 0.16 and 0.3 times 0.7. So, that sum is 1, this will be 0.21. You see this is increasing. So, first 0 and 1 was 0, this slightly more, slightly more, slightly more, and then you do 0.4, 0.6, that is equal to 0.24, larger, and then finally we have 0.5, 0.5, that takes us to 0.25, right, and then we will come back to this, right. So, now 0.6, 0.4 will be the same, 0.7, 0.3, 0.8, 0.2, 0.9, 0.1, and then 1, 0, right. So, among all of these you see that this is the largest, right. So, we can see that there is a way to solve the problem, but then we are trying all possibilities. Instead we can eliminate one of the variables over here. So, I can say I want to eliminate x2 in terms of x1, right. If I do that, I get a problem such as this, right. Let me erase some of this. Yeah. So, we have we can eliminate x2 by writing it as 1 minus x1, then there is only one variable unconstrained, or I can eliminate x1 in terms of x2, then the variable will be x2. So, by eliminating one variable with the help of equality constraint, we can make it unconstrained and solve the problem. Okay. If you now want to solve it, then we will immediately see, let us say this problem I want to solve. If you recall from our previous lecture on unconstrained minimization, if this is f, then the necessary condition is dou f by dou x1, which is in this case equal to we have x1 minus x1, that will be minus 1, minus of minus plus, that is x1 square, that will be 2 x1, that should be equal to 0, we get x 1 equal to half, which is what we found out, right. If x 1 equal to 1, based on this relationship x 2 is also this is x 1 equal to half, x 2 is also equal to half, right. So, it works out when you can eliminate one variable in terms of the other, we can reduce the size of the problem from 2 variables to 1 variable and we can solve it. But this type of elimination is possible only in some cases. If the equality constraint is complicated, let us say I give something like sin x into log x plus square root of tan x or something like that, I may not be able to solve it. I mean, I will say x 1, this is x 2 and this is let us say x 1 x 2, something like that. If that is my equality constraint, I may not be able to express one variable in terms of the other. So, we will not be able to do what we have accomplished here, that is eliminating one variable. Okay. So, we will discuss how we do it when that is not possible. Okay. Let us say we have a constraint which is not going to let us eliminate one variable in terms of the other, then what do you do? In that case, we go to the first order approximation. Okay. So, we think about this small perturbation. So, let us say that optimum is given by, let the optimum be x 1 star x 2 star. At that point we will consider this perturbation, okay. That is delta x 1, we say x 1 minus x 1 star, delta x 2 is x 2 minus x 2 star. So, that the new x 1 after perturbation is delta x 1 plus x 1 star and x 2 will be delta x 2 plus x 2 star. When we have that, then we can consider the Taylor series approximation of this function h. How do we do that? If I have h, let us say I want to do at x 1 and x 2, okay, which are given by this, then it will be whatever h is at x 1 star x 2 star, okay. This is 0th order term, right. So, this is 0th order term, right. Then there will be first order term. So, we have to perturb it by this much. Then what we say is that partial derivative of h with respect to x 1, evaluate that at x 1 star x 2 star. Okay. We are taking derivative with respect to x 1 partial derivative, but resulting expression we have to evaluate at x 1 star x 2 star, because that is what we said is optimum, and then this will be multiplied by delta x 1 and dou h by dou x 2, again evaluated at x 1 star x 2 star into delta x 2, and there will be order 2 and higher terms. Okay. So, this will be order 2 and higher. Okay. Why do we do this? Because we say that when we take the approximation of this equality constraint which is not amenable to eliminating one of the variables, then we take up to first order and make it equal to 0. That is, if you ignore all these higher order terms, then you make it 0, and this will be a linear equation in terms of the perturbations delta x 1 delta x 2. So, we can eliminate one perturbation in terms of the other. What we did the whole variable in the previous slide, now we are going to eliminate in terms of the perturbation. So, what we do is eliminate one perturbation in terms of the other, either delta x 1 delta x 2. So, that after perturbation our equality constraints remains again valid, meaning it should be equal to 0. What I wrote by hand, we are approximating, that is a symbol for approximation, h x 1 x 2, we are approximating 0th order term, and then the first order term that we wrote dou h by dou x 1 times delta x 1, dou h by dou x 2 times delta x 2, and that is it, the approximation. For first order we are stopping there, and then say that that should be equal to 0, that is after perturbation it should be 0. Now, this is 0 anyway, because if x 1 star x 2 star is an optimum, it must also satisfy the equality constraint. So, that is 0. So, what is left with, what we are left with are these two terms, the sum of these two terms should be equal to 0. These are the first order terms in two variable case, that should sum to 0. Therefore, by using this relationship we can get delta x 2 in terms of delta x 1 and some information that partial derivative with respect to x 1 evaluated at that point, partial derivative of h with respect to x 2 evaluated x 1 star x 2 star. Okay. So, now we are eliminating perturbations rather than the variable itself, it is an approximation, which is fine because the local minimum is always defined with respect to a local vicinity. So, taking first order perturbation is perfectly fine with that. So, the feasible perturbation is something that satisfies the constraint even after perturbation. That is what we are doing. We got delta x 2 in terms of delta x 1. Now, we consider similar expansion for the function. So, we have f at x 1 x star some value and then we have the first order term, the first one as it is. Second one, what we have done is the delta x 1 here, which would be basically this, right, that is what we have from here. So, that one we have replaced, this is nothing but delta x 2, right, that is what is here, we substituted there. Okay. So, that should be something that we should look at. What do we, if we say that this function here has to be a local minimum, then to first order we do not want any change in this, right, whatever we have put here that should not change to first order, because as we had discussed earlier for unconstrained minimization, when you have delta x 1, that delta x 1 may be positive, may be negative. So, sometimes f of x 1 x 2 may be larger than f of x 1 star x 2 star, sometimes may be smaller. So, first order we do not want the term to change. Second order will be there, that will be for sufficiency. First order we say that should be not changing, that gives us a condition to say that that should be equal to 0. This first order term should be equal to 0. Before we say that, we denote something that we have here. We have defined something called lambda here. See, dou h by dou x 1, this term is here as it is, but what we have is dou f by dou x 2 divided by dou h by dou x 2. So, these two we have defined as lambda along with the negative sign. That means that we have defined this lambda to be minus. So, notice that negative sign, dou f by dou x 2 divided by dou h by dou x 2, both evaluated at x 1 star x 2 star. Now, again go back, what we have defined, let me change the ink color, important, so I will put it in red. So, along with the negative sign, okay, so this whole thing is this lambda that we have, okay, that is lambda, right. So, lambda is minus dou f by dou x 2 divided by dou h by dou x 2. So, let me write it. So, here you see minus dou f by dou x 2 divided by dou h by dou x 2, both of which are evaluated at x 1 star x 2 star. So, this whole thing is evaluated at x 1 star x 2 star. Okay. So, that is what we have lambda. Lambda is defined that way, and then we said that dou f by here. So, this term here. So, we said that the first order term, this whole thing here, okay, that must be equal to 0 for, because for any perturbation delta x 1 we do not want the function to change. So, what we get here is that dou f by dou x 1 plus a lambda times dou h by dou x 1 equal to 0, that is what we have shown there, okay, the previous one. But the way we have defined lambda over here, that leads to this equation, okay, that leads to this equation. All right. So, if you look at this, this was the necessary condition when we eliminated delta x 1 and had only delta x 2 and had only delta x 1. This is the way we defined lambda. So, these two equations if you see, they have a pattern. This is dou f by dou x 1, this is dou f by dou x 2, this is dou h by dou x 1, this is dou h by dou x 2, both have lambda, same lambda. So, we got now two equations, okay, which are identical with respect to x 1 x 2. Now, this gives us a way of thinking about the necessary conditions. Dou f by dou x 1 plus lambda times dou h by dou x 1 equal to 0, dou f by dou x 2 plus lambda dou h by dou x 2 equal to 0. In both cases it is the same lambda. The way you define lambda is minus dou f by dou x 1 divided by dou h by dou x 1 or minus of dou f by dou x 2 divided by dou h by dou x 2. Okay, the same lambda for both, and this lambda is called the Lagrange multiplier corresponding to the equality constraint. We have an equality constraint, corresponding to that there is a lambda which is defined in this manner, which gives us the necessary conditions also. Okay. And think about what this Lagrange multiplier means. It shows that this is nothing but sensitivity. What do we mean by that? It shows that if there is a small change in the constraint, it tells you what change is going to be in the objective function with respect to that variable, for that matter any variable, because this is valid for x 1 and x 2. When you have more variables, the same trend continues, right. It is a sensitivity, it is a negative of the ratio of the change of objective function, rate of change of objective function with respect to a variable compared to the rate of change of the constraint. That is what is a Lagrange multiplier, a very important concept. Okay. And it is also useful to define what we can call a Lagrangian. Okay. Lagrangian. Lagrangian is defined as the function plus lambda times the constraint. Okay. When you do that, it becomes unconstrained problem in a way, because this is the original problem, these are original problem which had an equality constraint. Now, that problem is identically equal to just this minimize Lagrange respect x 1 x 2 objective function plus lambda times the equality constraint. Okay. If you were to write the necessary conditions for this problem, you would get exactly the same equation. Lagrangian derivative with respect to x 1 dou f by dou x 1 plus lambda times dou h by dou x 1, the same thing with the second equation also. So, we arrived at these equations in this way. Now, we are saying that we can also arrive at it in a different way, called using the concept of Lagrangian. Okay. And these are the necessary conditions. Now, the moment we say this Lagrangian minimum with respect to x 1 x 2 and there is this unknown multiplier. So, then we get these two equations, necessary conditions, and then we have the equality constraint anyway with us, h x 1 x 2. We have three equations in three variables. Our variables are x 1, x 2 and lambda, and we have three equations that we have in front of us. So, we are fine, we have as many equations as unknowns, and hence we can solve for them. Okay. This is how we deal with the constraints, equality constraints. There is a geometric interpretation to this. Let us say we take this two variable problem, we had f x 1 x 2, there will be contours as we have shown here in black lines. That is, for different values of f of x 1 x 2, we can draw these contours. So, f value on the contour on anything you take will be constant, okay, the iso objective function values. All right. Now, h x 1 x 2 as we said will be a curve, it can be a closed curve or open curve, which is shown here as a red one. Okay. So, in this case, where is the optimum? Because we say that constraint is such that everything because f increases from here, it increases this way, this is the minimum, but let us say constraint is such that we cannot go on this side of the surface. H, we have to be only on this side. This is our feasible space. Okay. Then unconstrained minimum is not accessible to us, we would keep on increasing. When you come to a particular point, we realize that that is the smallest f, because f increases as we go away from here. So, that is the smallest. If we move a little bit further into feasible space, then I would increase my objective function. Okay. So, geometric interpretation here, when we wrote that gradient of f plus lambda into gradient of h equal to 0, what we mean to say is that the gradient of f is compensated by this, it is on the negative side, right, lambda times gradient of h. Okay. So, geometric interpretation is that the contour of the equality constraint is going to touch here, it is a point that touches the contours of the objective function. Okay. That is a geometric interpretation of the Lagrange multiplier and the associated equality constraint. What if there are n variables in m equality constraints, right? We have n variables x1, x2, xn, and there is h1, h2, hm. We necessarily want m to be less than n, right. If m is equal to n, then as we had said in the case of one variable, one function, we will only have a few points, even if at all they exist, then we cannot do optimization. So, we need to have freedom. So, that is why we want m to be less than n. So, in which case we will let me erase it. Okay. When we say we minimize here, I am just calling x capital X, meaning that capital X is x1, x2, xn, and h is h1, h2, hm. If I want to solve a problem like this, I can solve only if this m is less than n, so that I have some freedom to search. Okay. So, here we are asking a question again, can there be more constraint than variables? The answer is no, we cannot have this is constraints, we cannot have more constraints than the variables. If m is greater than n, feasible values may not exist, even if they exist it will be a few discrete values. So, it is an over constraint problem, we cannot do optimization. When m equal to n, some discrete values may exist, but you can still not do minimization. In order to do minimization, we need to have m less than n. Okay, that is what we said. Now, when you have such a thing, what we did with the two variable case necessary condition, we create a general case. Now, I have x like uppercase, that means that I have x1, x2, xn, and then h also m. So, h1, h2, h3 up to hm, then the necessary conditions can be written like this. There is something called the gradient of the objective function and gradient of the constraint, equality constraint, and then we have this Lagrange multiplier vector, because with respect to each of these h's, h1, h2, hm, there will be a lambda 1, lambda 2, lambda m. So, and then we have the equality constraints itself. So, again if you count how many equations are there, there are n equations here, there are m equations here, total we have n plus m equations. How many variables do we have? We have n variables in x and then m variables for lambda 1, lambda 2, lambda 3 and lambda m, right. We have n plus m variables, n plus m equations, again we are fine. So, here also if you think of geometric interpretation, let us say we take a problem, here I have taken the same thing, but I am saying that instead of having only one equality constraint that is shown here, let us say there is another equality constraint, something like that. Okay. Over there what happens is the gradient, so this is h2, this is h1, right. Let us call this h1, that is h2. Then what we have here is that gradient of the objective function is a linear combination of this. What does that mean? It means that we have gradient of the h1 with respect to that x there times there will be lambda 1, there will be another one lambda 2 for the second constraint, and the gradient of the objective function, all of these with respect to this x here, they should sum to 0. So, if there is the gradient over here for the objective function like that, this red one may be like this, blue one may be like that. Okay. You have to draw the gradients properly. So, there will be sum of all the gradients should be equal to 0. Okay. Here we did not draw the thing properly, actually the blue one gradient will be like this, red one gradient will be like this. Let me change that to red color. Okay. So, let us say that gradient is like this, and the objective function will be sum of these two. So, the gradients of the two objective function this and this will be in the opposite direction to the gradient of the function. That is how we can interpret in multiple variables. If there are n variables and m equality constraints, m should be less than n. We will discuss how we can derive this in the next lecture. Thank you.